Hi, everyone. So when we defined double integrals earlier, we started off by defining them over rectangular boxes, and then we moved to general regions. And we said that we could define the double integral over a general region by defining a new function that agreed with the old function, but we set it equal to 0 if it was outside that region. So we could enclose it in a box. And then that function would be defined over the box. And so we could define it using the previous definition. There's a similar process that we could use for triple integrals over general regions. It's very, very similar. You take the region, you enclose it in a three-dimensional rectangular box, define a new function that's set equal to 0 outside of our region, and then we use the old definition in terms of a rectangular box. So I'm not going to go through that. It's in the textbook if you want to look at it. It's just kind of tedious, and it's so similar that I'm just going to skip that here. What I'm more interested in going over is the Fubini's theorem and the iterated integrals, because this is how you actually evaluate these. So there's a Fubini's theorem for triple integrals, just as for double integrals. And over general regions, it's similar to what we did for double integrals, where you fix one of the variables and then you let the other variable range between two expressions, between two graphs. It's just a bit more complicated with three-dimensional regions because there's one extra dimension. So what we want to do is think of if we can project this region onto one of the coordinate planes, and if that region itself then can be written as a type 1 or type 2 region, then we can kind of build our way up. So we can start with one variable, say, okay, this first variable is going to range from, say, 0 to 2. And then for, if we fix that variable and then let a second variable range between two different values of that a function of that variable, and that would give us a two-dimensional region. And then we say, okay, if we're in this two-dimensional region, then what would the third variable range between? And it could be a function of those two variables. So it's just a little bit more complicated because of this extra dimension, this extra step. And these are called iterated triple integrals. And I'll go through some examples. I did one example with each of the three different types. So there's three different possibilities depending upon which of the coordinate planes that you project onto. And then within each of those three, there's two possibilities depending upon the order that you want to do the type one, whether you want to do a type 1 or type 2 region. So overall, there's 6 possibilities. If you think of all the permutations of x, y, and z, you could have dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dz, or dz, dy, dx. And figuring out which of those 6 possibilities you want to choose is sometimes part of the problem. A lot of them can be done in more than one way, so that you could do them any of the different ways, but some of them you really can only do it one way. So let's look at some examples. So let me go down here and just show you the rest of this. So remember that when we're setting up the integral, we're going to be setting it up from the outside in. You start on the outside limits, and then you gradually move your way in, fixing more and more variables. But when you evaluate it from the inside out. You start inside, you do the innermost integral, and then you gradually work your way out. And your limits have to match the order of the variables in your integration. Otherwise, it's not going to make any sense. So these are called type 1, type 2, type 3 regions. Sometimes if you project onto the xy plane, that's sometimes called an xy simple region or just an xy region by other textbooks. Or if it's yz, then yz simple, xz, xz simple. Our book just used type 1, type 2, and type 3. But it's really not important, the name. I'm not going to test you. Is this a type 1 or a type 2? That doesn't really matter. What's important is that you are able to set up the limits correctly so that it matches the region, and then you're able to evaluate the iterated integrals. Okay, so let's look at our first example. Before we even set one up, I just want us to get some practice evaluating some of these triple iterated integrals, because it's a little bit more complicated than with the double integrals, although it's the same idea. So let's look at this iterated triple integral. So in this example, I'm going to really make it explicit, the brackets and the meaning of it. But in the next two examples and in the future, I won't use the brackets. I'll probably still label the limits just to keep that clear, but I'm not going to actually use the brackets. So here, we read from the outside in. So since the outside variable is dy, that means our first limit of integration is y equals 0 to y equals 1. So we have the integral from y equals 0 to y equals 1 of, now z is the next one going in. So that means we have the integral from z equals y minus 1 to z equals y of, and then finally x is the innermost, so the integral from x equals z to x equals y of xyz dx. The first bracket closes off the x integral, and then dz. The second bracket closes off the z integral, and then finally we have dy. So if you think about it, we're projecting onto the z, the yz plane here. So this would be actually, if this is a type 1, type 2, or type 3, this is a type, or this would come from a type 2 region or a yz simple. So projecting onto the yz plane. Okay, so how we do these, we start on the inside and work our way out, just like we did for double integrals. So we're going to start with this one. We're integrating with respect to x. So that means this is going to integrate to x squared yz over 2. In fact, let me take that factor of a half out right now so we don't have to deal with it. I can take it all the way out since it's a constant. Okay, I still have all this stuff. And I've got x squared yz evaluated from z to y. Okay, so this is 1/2 the integral from 0 to 1, integral from y minus 1 to y. So this here, I'm substituting in for x. That was the innermost variable. That means y and z are constants. So y and z just tag along, and I get y squared minus z squared dz. Okay, let's move down here. If I were to FOIL this out or distribute, this would be y cubed z minus yz cubed. So I'm going to go ahead and just rewrite that there just to save space. Now I'm integrating with respect to z. Okay. So this integral with respect to z is going to be y cubed z squared over 2. And then minus y z to the 4th over 4. And it's evaluated from y minus 1 to y. Okay, now there's a couple things we could do here to make our life a little bit easier. One thing we can do is get a common denominator. So this is 2/4. And then we can take that 4 outside. So that's going to make 1/8 on the outside. And then I can also factor, a yz squared. So that might also help. So let's go ahead and do both of those things. Factoring out 1/8, or factoring out 1/4, getting 1/8 now on the outside. And we've got, if I factor y z squared. What am I left with? 2y squared minus z squared, right? Right. From y minus 1 to y. Again, the middle variable here was z, so we're substituting in for z. Y is a constant here, so that's just going to tag along. So we got y times, so now I actually have to substitute in for z. So when I substitute in y, I will get y squared times 2y squared minus y squared, which will be another y squared. So it's going to be y squared times y squared, and then minus y minus 1 squared times 2y squared minus y minus 1 squared. Okay, so this one is a little bit trickier. I probably don't have the right number of parentheses here. Let's see. Yeah, I think the brackets. Let's clean this up. That's y to the 4th. Oh boy, let's see. Why don't we do this stuff here? This is 2y squared minus y squared plus 2y minus 1 after distributing the minus. So that's going to be y squared plus 2y minus 1. Okay. All right. I don't want to do too many steps at once or I'll confuse myself here. Okay, we got y to the 4th minus y minus 1 squared times y squared plus 2y minus 1. I mean, this is really, this is the tedious part. This is not calculus. This is a polynomial. So, I mean, the only way you can mess up integrating a polynomial is if you make some silly algebra mistake. So, not really worried about this step. It's that you understand how to evaluate the process. Okay, this is y squared minus 2y plus 1. What do these two quadratics multiply together to get? Let's see. I'm going to drop the y now. Since we are down to just one variable, we've got y times y to the 4th minus, oh boy. Okay, so we got to distribute y squared minus 2y. I'll make a minus 4y squared plus 2y, and then plus y squared plus 2y minus 1. Good grief. Good grief, Charlie Brown. Yeah, let's see. After we distribute the minus, the y to the 4th minus y to the 4th will cancel. We also have the 2y cubed minus 2y cubed. Those go away. Y, okay, a lot of stuff cancels out. That's nice. Okay, so it looks like these do not cancel out, plus 4y. So we're left with a plus 4y squared, after, remember the minus here, minus 4y plus 1. How much room do we have here? Oh, not much. Okay, well, we're just about done. So altogether, it's 1/8 the integral from 0 to 1, 4y cubed minus 4y squared plus y. Yeah. We have enough room to finish this. No problem. 1/8. We're evaluating y to the 4th minus 4y cubed over 3 plus y squared over 2 from 0 to 1, which is 1/8. 0 is not going to contribute anything, so we get 1/8, 1 minus 4/3 plus a half. We get a common denominator of 6. How much do we have on top here? 6. 6 minus 8 plus 3. That's 9 minus, that's 1. So 1 over 48. That is the value of this iterated integral. All right, so that is just some practice evaluating these. Of course, what we want to do is actually do some problems where we have to set these up and then evaluate them. So the next problem we're going to look at is just finding a volume. This one is going to be pretty messy. I think I can get through it on one page if I write small. We're going to be finding the volume between two quadric surfaces. So let's take a look at that. So there's even a picture. I got this from a different textbook, and I scanned the picture and put it into the PDF. So it's the volume of this region E enclosed by the surfaces. So the bottom surface is Z equals x squared plus 3y squared, and the upper surface is 8 minus x squared minus y squared. And you can see here they intersect in a particular curve. So let's figure out the projection onto the xy plane. So how do we figure out the projection on the xy plane? Well, we need to see what the intersection is. So if we were solving just this like a system of two equations to figure out what the intersection is here, then z, which is x squared plus 3y squared, would have to be equal to 8 minus x squared minus y squared. So let's set those equal to each other. If I add x squared and y squared to both sides, then I get that the curve of intersection is 2x squared plus 4y squared equals 8. And if after I divide by 2, I get x squared plus 2y squared equals 4. So that is the curve in the xy plane. That's the projection of the curve of intersection onto the xy plane. Now, what is the next thing we need to do? Well, see this projection here in the xy plane. That's an ellipse, right? X squared plus 2y squared equals 4 is an ellipse. So this is a type 1 or xy simple region. So we have to think about how we would do this region as if we were doing a double integral in the xy plane. Let's start off by letting x vary. So where does x vary between? Starts all the way over here at -2. So here's x equals -2, all the way over to here, which is x equals 2. So x varies from -2 to 2. Remember, your outermost variable is always just constants. It's just from a number to a number. So we're setting up the integral now. We got the integral from x equals -2 to x equals 2. Then we need y to vary. So where does y vary? So they actually kind of show you here. Well, you have to solve for y in this ellipse equation. So if I solve x squared plus 2y squared equals 4, I'm going to get 2y squared is 4 minus x squared. I'll just write it on the side here. We get 2y squared is 4 minus x squared. And after I divide by 2, y squared is 4 minus x squared over 2. So y is plus minus square root of all that stuff. So this is where it gets a little bit interesting. We got y going from minus root 4 minus x squared all over 2 to y equals root 4 minus x squared over 2. Now, something you might notice is our limits are symmetric, right? We got -2 to 2, minus this to this. That means when we're integrating these later, it's going to be possible to use even properties of functions. And so we'll be able to cut down on the calculation a little bit. Okay, and then where does z go from? Well, as they have here, we have a fixed xy. So imagine going then from this point and then go up along this line. The region, you enter the region here at the lower surface. So at x is x squared plus 3y squared. And you exit the region up here. So we go from here all the way up to here, 8 minus x squared minus y squared. Now, fortunately for us, it doesn't say to integrate, an actual function. It doesn't say integrate x or integrate xy. It just says find the volume of the region. Well, to find the volume, that's just the integral of dv. So it's just integrating the function 1. So we just have dz, dy, dx. Check your order. As I go in, x, y, z. So from the left to right, x, y, z. as I start on the right and I go in x, y, z. So x is on the outer, y is in closer, and then z is the innermost. They have to match up like that. Okay, so when we first start off here, we're just integrating 1. Well, that's just the length of the interval. Now here, they're expressions, but still, it's just going to be the upper limit minus the lower limit. So that's going to be 8 minus x squared minus 3y squared. So that's 8 minus 2x squared minus 4y squared dy dx. All right, now there's a couple things we can do here. I'm going to move us down a bit since we already kind of used the picture. Notice that this, we're integrating with respect to y, and there's only one y term, which is y squared. So this is an even function. Okay. So we're integrating an even function from minus a number to plus a number. That means we can factor out a 2. But also, notice 8, 2, and 4, we have a common factor of 2 there as well. So I'm going to actually do a little bit of skipping some steps here. I'm going to factor out the 2 from each term, and then I'm going to take out a 2, and I'm going to make this lower limit 0, the lower y limit. So it's going to be 4 times the integral x to minus 2 to 2. And now y is going to go from 0 to this root. And we're only integrating 4 minus x squared minus 2y squared, which is a little bit nicer, dy dx. Okay, again, you don't have to do that, but it's just going to make things a bit cleaner. All right, so let's integrate with respect to y. We got 4 minus x squared. That's all a constant. So all of this is just going to integrate to 4 minus x squared times y. So 4 minus x squared y, and then minus 2y cubed over 3. All right, and this is evaluated from 0 to, I'm going to start writing this as 4 minus x squared over 2 all to the 1/2. So I'm going to start using fractional exponents here. And you'll see why in just a second. Okay, let's continue. If I substitute in 0, this is the whole point of using the even property, is I don't have to worry about that limit. So let's substitute in here. So we've got integral -2 to 2. And it's 4 minus x squared. Let's see. So we substitute in here for y. Okay, it's going to be 4 minus x squared times 4 minus x squared to the 1/2 over 2 to the 1/2. So that's going to be 4 minus x squared all to the 3/2 over square root 2. Everybody okay with that? Substituting all this in for y. And then we've got minus 2/3. And when we substitute in here, it's going to be 4 minus x squared over 2 all to the 3/2. So you see why I used fractional exponents. We see that these are really like terms in terms of 4 minus x squared to the 3/2. We just need to figure out what the coefficient is. So that may be a little bit tricky. Let's see. So it looks like it is, I'll just write here, coefficient of 4 minus x squared all to the 3/2. It's 1 over root 2 minus, let's see, we've got a 3 on the bottom, and then we have 2 over 2 to the 3/2. So that's overall that's a square root 2 in the denominator. So 1 over 3 root 2. Okay, that's not that bad, because this is really, if you factor out 1 over root 2, it's just 1 minus 1/3, which is 2/3. So we end up getting root 2 over 3. Okay, so that means we can clean this up a bit more. Take this coefficient out, and let's combine it with the 4. And so we're going to have the 8 root 2, sorry, we're going to have 4 root 2 over 3 times the integral from negative 2 to 2 of 4 minus x squared all to the 3/2 dx. Okay, again, this is an even function. So we make our life a little easier by using that property. So we'll get another factor of 2. This is going to be 8 square root 2 over 3 times the integral from 0 to 2 of 4 minus x squared to the 3/2 dx. And now we have a little bit of work to do. Because this is a quadratic, we have to use a trig substitution. So what trig substitution are we going to use? We need x to be 2 sine theta. If you remember trig substitutions from Calc 2, if it's a squared minus x squared, you want to use a sine theta, which means that dx is 2 cosine theta d theta. Okay. And I'm going to change the limits at the same time. Okay. So this gets a little involved here. When x is 0, that means sine theta has to be 0, which means theta is 0. And when x is 2, sine is 1, so theta is pi over 2. So we're integrating now from theta equals 0 to pi over 2. All of this is 4 minus 4 sine squared. So this is all 4 cosine squared. And then we're raising it to the 3/2. So that's going to be 4 to the 3/2. Oh, I left off my constant. Let's not forget our 8 root 2 over 3. Sorry about that. So we have 4 to the 3/2, which is 8. So let's just write 8. And we've got cosine squared to the 3/2, which is cosine cubed, times dx. But dx from the substitution is 2 cosine theta d theta. Oh boy. So what we end up getting, after we pull all the constants out, we have 8 and 2. So that's going to make 128. 128 root 2 over 3. The integral from theta equals 0 to theta equals pi over 2 of cosine to the 4th. Okay, now the best way to do this is to use some identities. You could use like reduction formulas and stuff, but just on the side here, I'm just going to derive kind of what cosine to the 4th is. So cosine to the 4th is cosine squared squared, which is 1 plus cosine 2 theta over 2 all squared, which is 1/4 times 1 plus 2 cosine 2 theta plus cosine squared 2 theta. And now I have to use the identity one more time. 1 plus 2 cosine 2 theta plus 1 plus cosine 4 theta over 2. You're probably having not so nice flashbacks to trig. What do we have inside here? We got 1 plus a half. So that's 1 plus a half is 3/2, but then it's times a 4th. That's 3/8. Plus 1/2 cosine 2 theta plus a 4th times, so that's 1/8 cosine 4 theta. All right, so now we can substitute this expression in, and okay, it looks like we don't have much room, which we don't, but a lot of this is going to be okay because we're integrating from 0 to pi over 2. Okay, so 128 root 2 over 3. Okay, so I'm just imagine this is up here. So how does this integrate? It's going to integrate as 3 theta over 8 plus then we get sine 2 theta. We pick up another factor of 2 on the bottom, so plus sine 2 theta over 4 plus 1/32, because we pick up a 4, sine 4 theta over 32. And this is all evaluated from 0 to pi over 2. Notice 0 goes away because we get 0, sine 0, sine 0, sine of 0, 0. And in fact, these two go away as well, because the second term would be sine of pi, the third one would be sine of 2 pi, and the sine is equal to 0 at any integer multiple of pi. So really, it's just this term evaluated at pi over 2. So that's 3/8 times pi over 2. So not that bad. Let's see. 3's cancel. 16. These are all powers of 2. So this is leaving an 8 on the top. So altogether, we've got an 8 pi square root 2. Okay, so you can see these problems can get kind of tedious. There's a lot of algebra, and especially if you have to use an integration technique. So on an exam, what I might do is just ask you to set up the iterated integral, but not to evaluate it, because that way I don't want to test your ability to do Calc 1 stuff and algebra for 25 minutes just to see if you make a mistake 5 minutes in or something. So if it's anything approaching this amount of messiness, then I might just ask you to set it up. All right, we're going to do one last example where we are actually going to integrate a function, not just one. It's going to be over a tetrahedron region. So evaluate the triple integral over tetrahedron with vertices at the origin and the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, so let's draw this first. So that's what the tetrahedron looks like. Since we've already done type 1 and type 2, let's do this as a type 3. Let's project onto the xz plane. Everything is symmetric in x, y, and z, so really, except for the integrand. But as far as setting up the limits, it could be on any of the planes. But let's do type 3 xz. So project onto the xz plane. So we have to stop and think about what this looks like in the xz plane. So I'm going to draw a little picture of the xz plane. Okay, so you have to kind of imagine this turned around. So turn the tetrahedron around and imagine that you're looking at the xz plane from the kind of the left side there. So make sure you got the positive directions going the right way. So here's 1, here's 1. And so it's this region. Let us fix x first. Okay, so we're going to fix x. Where does x go between? X goes from 0 to 1. For a fixed x, where does z go between? Well, it's going to be this. So the lower limit here is clearly 0, but what is that upper limit? Well, we need to find the equation of this line. This line here has equation x plus z equals 1. So if we solve that for z, that means z is equal to 1 minus x. So z goes from 0 to 1 minus x. And then now think of a point here in the xz plane, and it needs to shoot out from 0. So this face is in the xz plane. So y is going to start at 0 and shoot out all the way to a point on that opposite face. And since this tetrahedron has equation x plus y plus z equals 1, you can plug in all 3 points and see that that's the case. If you didn't know that, you could just find the plane that goes through 3 points. But each of those x, y, z coordinates adds up to 1, so that has to be the equation. So y goes from 0 up to, if I solve for y, it's going to be 1 minus x minus z. And we're integrating x, and then, again, the order innermost is y, then z, then x. Now we're integrating first with respect to y, but this is x. So that is a constant with respect to y. So the very first integration is going to be very simple. We just get x times the length of the interval, which here is 1 minus x minus z. So we have the integral from 0 to 1, integral from 0 to 1 minus x, and then we're integrating 1 minus x minus z minus 0 times x dz dx. Okay, so that's the first integration. Now we're integrating with respect to z. So let's see, how do I want to do this? Let's write this as x minus x squared minus xz. And then let's integrate with respect to z. We have to evaluate this from 0 to 1 minus x. We're finally down to one variable, so I'm going to drop the x equals. So this is the integral from 0 to 1. The lower limit, when I plug in for z, there's this factor of z in all of them, so that goes away. So it's, and actually here, this is x minus x squared times z. So it's really x minus x squared times 1 minus x, and then minus x 1 minus x all squared over 2. So again, a lot of tedious polynomial calculation. So let's see, let's just multiply stuff out. X minus x squared minus x squared plus x cubed. And what have we got here? Minus x times 1 minus 2x plus x squared. And then all over 2. Okay. This should be enough to kind of, already we should be able to collect like terms here. How many x cubes do we have? We have an x cubed. When we distribute here, we have minus 1/2 x cubed. So that's going to leave an x cubed over 2. Okay, so that goes away. X squared. So we have a minus 2x squared. And then we have here a plus 2x squared over 2, so plus x squared. So that is going to make minus x squared. And then we have x and minus x over 2, so that's plus x over 2. Okay, so that's all the terms collected together. This is pretty straightforward now. So it's just x to the 4th over 4, so we get x to the 4th over 8 minus x cubed over 3 plus x squared over 4 from 0 to 1. So 1/8, just down to fractions, 1/8 minus 1/3 plus 1/4. It has a common denominator of 24. 3 minus 8 plus 6. That's 1. 1 over 24. All right, so that is general triple integrals. Kind of tedious, kind of messy. And the trickiest part is probably setting them up. In the real world, you know, if you find the limits, there's many different tools online that would allow you to calculate triple integrals once you actually find the limits. But it's the process that's important. And we're going to do some triple integrals. We're not done with triple integrals. We're going to do triple integrals in cylindrical and spherical coordinates. And then when we get to vector calculus, that involves triple integrals as well. So we are not done with these triple integrals. We'll see them again.